wording for this. Thanks.
Maybe I just
No problem. For the next, yeah, web page, it's just wording. No change in substance. We can start, yeah. Okay, guess we're on. All right, we'll start by reviewing what we did last time. We finished a topic that's an IV model with velocity saturation, right? And the model starts with a velocity electric field model that's piecewise. It follows a certain equation and then saturates at saturation velocity, right? I think so. This is the model we followed. Follow this line up to this point, and then stays here. Okay. In this particular model, just to remind you, E set is equal to 2 times V set divided by mu, all right? Mobility. Using this model, we ended up with 2 IV equations. One IV equation is what we call equation A, which by itself is kind of interesting to remember because it's really very simple. It's the old current, mu C W L Vg minus Vt minus Vd over 2 times Vd. It's old current reduced by this factor, 1 plus Vd over E set L. Right? That's not too hard. And this current is good before we reach velocity saturation. The second equation we got, it was a surprise. By looking at the current near the drain, we concluded current must be smaller than or equal to W times V set times Cox Vg minus Vt minus Vd. But after thinking about that, I hope you agree this actually makes a lot of sense. The intercept of the two, we argued, gives us ID set and give us Vd set. So according to this model, the current looks like this. All right? Now, what's interesting is the equation for ID set and Vd set are not too difficult to remember, and I recommend you try to memorize them. Vd set is the average of 2 voltages. One is the classical Vd set, Vg minus Vt. The other is a voltage that's E set times L. You kind of expected L to be in here, and the only thing to make a voltage out of L is to multiply it by the saturation field, of course. So Vg minus Vt times E set L divided by Vg minus Vt plus E set L. All right? That gives us the voltage. And the general characteristics is always less than Vg minus Vt. And in fact, when channel length is smaller, this Vd set is smaller. In the extreme case, Vd set becomes insensitive to Vg, and it becomes proportional to L. All right, so that's the sensitivity of Vd set to L. Now, ID is probably even more important expression. If you can remember this, then you have a model in your head about what determines the ID set. There are 2 ways to 2 forms. Let me emphasize the second form. Although it looks complicated, maybe easier to memorize because it's made of the old ID set, W over 2L mu C Vg minus Vt squared. That's the classical ID set. Is that right? And the classical ID set is reduced by this factor 1 plus Vg minus Vt over E set L, the ratio of the two voltages. One voltage is always E set L, the other voltage is Vd minus Vt, 1 plus Vg minus Vt E set L. Okay. We look at two extreme cases when channel is very long. In other words, E set times L much larger than Vg minus Vt. So therefore, this term is negligible. Then ID set reduces to the usual long channel model. Specifically, it predicts that ID set is proportional to Vg minus Vt second power, and L inversely proportional to L, right? And for the very short channel case, then ID set is just proportional to Vg minus Vt to the first power, and also is insensitive to L. Okay, now that's extreme case. In between case, of course, is still a function of L, of course, all right? Okay, any questions about this model? Okay. This has been found to be a very good model, capturing the velocity saturation effect quite well, all right? Now, last time I asked you a question, and let's think about a question for now, all right? The question I ask you is, you know, we say there's a long channel range, short channel range. In the long channel range, ID set is proportional to Vg minus Vt second power, the so-called the parabolic relationship. And then in the short channel case, Vg minus Vt is or ID set is proportional to Vg minus Vt to the first power. So we use the term long channel and short channel. Similarly, we say when channel is long, Vd set reverts to Vg minus Vt. When channel is short, Vd set is quite small. So how long is long? How short is short? I ask you this question. Do you have a question? Do you have some answer for me? How long is long channel? Is 2 micron long? Is 1 micron long enough? Is 0.2 micron long enough? How do you decide what is long channel, what is short channel? When it's appropriate to use the long channel approximation, when it's not? You have an answer? No? Okay. Well, if you look at this equation here, you will notice when we say long channel, we always said it's E set times L larger than Vg minus Vt. When we see short channel, E set times L is much smaller than Vg minus Vt. So what makes channel long and short? Actually, there's no absolute value. It depends on Vg minus Vt. And there's an interesting lesson here. That is, even with 0.2 micron channel length, actually the transistor IV curve behaves just like our classical model in the range of Vg not being very much larger than Vt. Did you follow that statement? Even when the channel is very short, there's always a range of Vg close to Vt where the channel behaves very much like long channel transistor. Specifically, Vd set will be equal to Vg minus Vt, and ID set will be proportional to Vg minus Vt to the second power. Now that alone is interesting fact, because a lot of the design, of course, you know, low power design. I don't mean low power physical design. I'm particularly thinking about analog circuit, where you bias the transistor really at only Vg plus equal to Vt plus 100 millivolt. So in that case, the transistor does behave just like long channel transistor, and that's a fortuitous thing, because designers often still like to use this parabolic relationship between current and Vg and make a lot of design consideration based on those simple models. It happens to work. It works. All right? So that, I think, is the best answer to the question, how long is long, how short is short? Well, the fact is that even 0.2 micron device, you can say 0.1 micron device, can behave like a long channel device as long as Vg minus Vt is small enough. In other words, in this region of the IV curve, the transistor always behaves like a long channel transistor. Is that right? Okay. Of course, if the L is truly long, then this entire region behaves like an on-channel transistor. You know that, right? But most of the transistors here, you do see Vg minus Vt to the first power. So you cannot say they are long channel transistor. And yet, when you look at here, it reverts back to the long channel transistor behavior again. Okay? And for analog designers, this can be really a benefit. For digital circuit designer, where this is important, it's certainly much better to think that ID is proportional to Vg minus Vt to the first power. And the equation that we derived last time covers both regions smoothly. You don't have to make an assumption. They actually go from one extreme to the other smoothly. All right? Okay. Any questions? All right, let's move on to another topic. It's kind of a logical topic. We already figured out the ID set and the VD set. And now we talk about this non-saturation beyond the VD set. In other words, so-called early effect. And many of you think of it as channel length modulation. That's fine. Okay, so the question is, how can we understand what is causing this current to continue to rise? Qualitatively, we have already discussed this before. It's because channel length modulation, as VD increases beyond the VD set, there will be a finite distance of the channel consumed by that pinch-off region or the velocity saturation region. And the remaining portion of the channel, which determines ID set, effectively has a shorter channel length than L. That reduction of channel length is called channel length modulation, and it's that reduction of the effective channel length that's making or allowing the current to gradually rise, right? So the mechanism is there, and today we're going to look at a quantitative model for that. So if you want to be able to predict this, then how do you do that? The reason this is important is because this output conductance turns out to be very important for analog design, analog circuit performance. We want the slope to be small. We want the slope to be as small as possible. If we have perfect saturation, we can design circuit with very high gain and very good performance. But when this output conductance is large, the transistor's voltage gain is smaller, right? And let me not say too much about this introduction. Later, if there's a question, we can discuss that. But let's just get into this model right now. We want to model about this output conductance, right? In a way that we think is quantitatively worth your trouble to go through. Okay. Now, before we start that, let me clarify what we said about how channel length modulation or channel length reduction can cause the ID set to increase. Let's just go back to this equation that we just reviewed. ID set is equal to W mu C over 2. Instead of L, we say it's L minus delta L, whereas delta L is function of VD. So today we're going to find out how does this delta L, this velocity saturation region length or pinch-off region length, vary and increases with increasing VD. We want to find that. If we know the relationship between delta L and VD, then we certainly know how ID set will change with VD increase. Is that right? Because VD changes delta L. Right? The only thing I want to remind you here is that actually L appears twice on the right-hand side. Once here, once here. Okay? But that's a minor thing. All right? All right, so how are we going to solve this question on the lower left corner? Okay, how do we find delta L's function VD? Well, turns out we're going to do this using a very similar technique that we use to model the short channel effect or the drain-induced barrier lowering. We call it a quasi-2D analysis, right? So the approach we're going to use is very similar to the approach we used to derive that drain-induced barrier lowering equation 5.46, all right? And we're going to go from beginning with you. And we do that by drawing a Gauss box. Do you remember? Yes? Right? The left-hand side Gauss box turns out to be exactly the same. We won't bother with that. That is the electric field going in, electric field going out, electric field going in from the oxide, and the electric field going in from the bottom is 0. After you have done that, you may or may not remember, we end up with this. All right? Just take a look at this, see if it looks familiar. This is the difference of the electric field going in from the left and going out on the right. Give us this term. Right? This next term is the electric field going in from the oxide. Remember, the electric field going in oxide is equal to oxide voltage divided by oxide thickness. Oxide voltage is equal to Vg minus VFB minus 25B minus channel potential. Yes? All right? Okay? And this ratio of dielectric constant, of course, we know. The difference, turns out, is on the right-hand side. All right? The right-hand side, in some sense, is easier. So you can say well, maybe not easier, maybe it's a slightly more complicated. Let me explain to you what we're talking about. Two things. Let's remember what we need on the right-hand side. What we need on the right-hand side is all the charge in the Gauss box. Is that right? All the charge in the Gauss box. In this Gauss box, Gaussian box, right? That's what we're looking at here. Is that right? All the charge in the Gauss box. Yes? All right. Let's first look at the first component. First component is depletion charge. Now, we all know how to calculate the depletion charge. It's equal to Q times NA, of course, also divided by epsilon, and times the height of that Gauss box. Now, here's a difference between the way this model is set up and what we did for the drain-induced barrier lowering. A test for you. Do you remember the depth or the height of the Gauss box used in the analysis of drain-induced barrier lowering? Do you remember? What did we take as the height of the box? XD max, is that right? Yes, and we kind of argued that. But remember, all we wanted really is just a line where there's no electric field going in. Is that right? And we also want this line to be more or less horizontal. Is that right? And we already argued that line we're not very happy with because near the drain we really don't know where we should draw that. Okay? Now here we're drawing you a different such line. And let me tell you what it is. First, remember, we're not looking for this line to go all the way from source to drain. Why? Because we're only trying to analyze this problem in a short distance from the drain. Do you see what I'm talking about? We're trying to analyze channel length modulation. And this probably only exists in a short distance within the drain. Yes? Yes? So unlike the previous problem where we try to find the potential all the way from the source to the drain. Is that right? Here we're looking at a much smaller region. Yes? So in that case, we certainly can re-examine, is XD max still the best place to draw that line to give us the box? Chances are it's not. If it's not, can I suggest a better line? I can. The fact is that any electric field line, we can choose any electric field line. Along any electric field line, as you know by definition, the normal field will be 0, right? Any field normal to the field line is 0. Do you remember this concept from electrostatics? If you have two electrodes, let's say two electrodes, and they draw a lot of electric field lines, right? Field line is the direction of the electric field, right? Field line follows the direction of electric field, which means there will be 0 component of transverse field along this line. All right? So we can choose any field line as our bottom box. But let's remember, there's a second requirement for this bottom of the box. One is there's no normal field. The other is it should be more or less horizontal, parallel to the surface. Is that right? So any field line won't do. But take advantage of the fact we know we have a junction that's fairly sharp. Near this sharp junction, you can probably imagine there are probably a lot of electric field line going out all directions. Think about lightning rod. We know this concept. You have a sharp point, electric field lines goes all out. Is that right? And of course, these are to some extent hindsight that after we know this works, I'm telling you as if you should have thought of this easily. It's not. This takes many years. People are thinking about this. Eventually, this is what concluded. And this can also be verified, by the way, by just solving the Poisson equation using a 2D Poisson equation solver. If you've done that, you will find there's always electric field line fairly parallel about the junction. So for that reason, we take approximation that we can find such an electric field line that's pretty more or less flat to the surface about the depth of xj. See the point? Yes? As I said, it's kind of hindsight. If you have seen a lot of simulation results, you will also make this observation. Yeah, it's not too hard to find electric field line that's more or less flat over this distance at around xj. This distance is very small. Again, let me remind you. All right? Okay? Questions about the choice of this number? Okay, good. So we choose this xj as the bottom of the Gauss box. Therefore, the charge in this Gauss box is equal to Q, Na, xj, and of course you say, how about delta y? How about w? They have already been divided to the left-hand side, right? That's why I have a dy here. That's the delta y for this volume, right? W also has been canceled out. Okay? All right. So that's the depletion charge term. The next charge is even more interesting and very clever. You see, the problem we solve for the channeling J-induced barrier lowering, we implicitly assume, maybe explicitly assume, we're dealing with subthreshold region. Is that right? Subthreshold region. In the subthreshold region, VT is less than, VG is less than VT, or maybe just equal to VT, if we use that to model delta VT. Therefore, do we have a large current or not? We don't have a large current. If we don't have a large current, do we expect to have a large density of a mobile carrier? No. On the other hand, now we're trying to model velocity, channel length modulation, model the output conductance, the IV curve. Can we still limit ourselves to small Vd? We better be able to cover quite a range of Vg, right? Not small Vd, I don't mean. I mean, can we limit ourselves to small Vg? No, we have to deal with large Vg and large Vd. Is that right? Yes? When Vid is large, well, I should say large Vg and large Id. When Id is large, can we assume there will be no mobile carrier in this pinch-off region? Can we assume that? You cannot. You bet you cannot. In fact, later I'm going to give you some argument right now. I'll give some argument right now. I'm going to tell you the charge density here could be very close to charge density near the source. I know this is going to surprise you, but this is a fact. Now, if someone asks you, or I ask you to estimate or compare the charge density in here and at the beginning of the pinch-off region, can you make this comparison? This is the way you would compare. Here, the charge density would simply be equal to Cox times what? Vg minus Vt. That's it. Yes? Here, the charge density will be equal to what? Cox times, fill in the blank for me, Vg minus Vt. Very good, minus Vd set. How about that? Yes? Yes? All right, before I ask you to make comparison, well, first I'll just let you make a comparison. Comparison is, what's the ratio? I don't need a big accurate number. I just want you to tell me it's going to be a factor of 10 difference, or could be even only a factor of 2 difference, or even less difference than that. Right? Depending on what your Vg is, what Vd set is, right? They don't have to be that different. Factor of 2 is very reasonable. Right? Are you following what I'm saying? Yes or no? Let's see. Vg minus Vt is only, by the classical model, by the way, this will be 0. But this is not a classical model. This is what you have to remember, right? For Vg minus Vt equal to, let's say, 3 volt, suppose V minus 3, this may be only 1.5 volt. Remember, that's why I gave you some examples before. VG minus VD set is significantly smaller than VG minus VT. Not equal to minus VT, and significantly smaller than VG minus VT, right? So suppose VD set is 1.5 volt. Then here is Cox times 1.5. Here is Cox times 3. So what do you conclude? So the difference is not that large, number one, correct? Number two, this is the really interesting question. What about the charge density, not so much the charge density in volume, charge density in per area, let's say, what we call the Q inversion. What about the charge density here? Way into the pinch-off region. In fact, almost at the edge of the M plus junction. What can you say about the charge density there, the mobile carrier? How does that compare with the mobile carrier density at the edge of the pinch-off region? In terms of per centimeter per square centimeter, centimeter squared, not centimeter cube. In other words, the usual unit we use for Q inversion. We're counting per area, right, not per volume. Any suggestions? I'll give you the answer, and I'm going to ask you for a justification. The answer is the charge density here is exactly the same as charge density at the beginning pinch-off region, namely exactly the same number we wrote down before, which is only half of the charge density source. And that charge density remains constant throughout the velocity saturation region. Now give me an argument for that, justification for it. Yes? Patrick, is that right? All right, please.
If the velocity is the same and you know the current is the same by current continuity, then the charge density has to be the same.
Yes! All right, okay. That's exactly right, all right? That's exactly right. So, you know, we can understand what goes on in the transistor. We don't have to, you know, just follow along with the very simple picture that we picked up maybe along the way somewhere. We actually can know what it is. And particularly, we have to remember the charge densities throughout this channel, including pinch-off region, may not differ that much from source or drain. May not. Is it okay now? So hopefully that will really shatter this concept of pinch-off region. What is pinch-off? Do we really not have any mobile carriers, or do we have lots of mobile carriers? All right? Okay. So let's agree we have lots of mobile carriers. Then we cannot ignore that in this in the charge term for the within the Gaussian box. Is that right? We have to include that. But fortunately, we know that's not important because we don't need to know its vertical distribution. All we need to know is all the charge in the Gauss box. Doesn't matter whether spread out from the surface into the, you know, somewhat the first 200 angstrom or not. Doesn't matter. And we'll see how to deal with that next. All right? Any question about the first equation, first step? If not, let's look at the second step. Second step, we just replace the dE dy by d square v dy square. Any problem? All right. Okay. And by the way, we use y prime because we define our coordinates in such a way that 0 is here. Okay, at the beginning of the velocity saturation region, we don't want to put 0 at a source. In fact, this whole equation, we're not going to solve it from all the way from source to the drain. We're going to solve from the beginning of the pinch-off region to the end of the pinch-off region. Okay, that's why we call it y prime. All right. Okay. The more we limit the range we have to solve the equation, the easier and the more useful approximations we can make. Right. So we limit ourselves just within this pinch-off region. Next term, no change at all. The right-hand side, we did change things quite a bit. Now, how did we get to that? Now, where we get to that is really very clever. What we did is this. We know this first equation is good throughout this pinch-off region. Is that right? So we're going to evaluate this first equation at y equal to 0, at y equal to 0, at the beginning of pinch-off region. Are you following me? All right. At the beginning of the pinch-off region, we can argue the first term is still negligible. In fact, this is what's generally known as the gradual channel approximation, is that we don't worry about the electric field in this source drain direction. We only worry about electric field in the vertical direction. That's what's giving us this result of Q inversion is equal to Cox Vg minus Vt minus V. All right, by the way. This usual equation we've been using, although we didn't spend a lot of time justifying it. But if you try to justifying it, it's because we ignore this first term. We reduce it to a one-dimensional problem, only looking at the vertical electric field, how that's conserved, right? Or the charge, or the electric field must end on charge. We end up with that. But if we consider the second dimension, then the charge will not be just equal to Q inversion Cox Vg minus Vt. Today, I'm not questioning this approximation, Q inversion equal to Cox Vg minus Vt minus V. It's a very good approximation, but only good in this region, between the source and the pinch-off region, not within the pinch-off region. Within pinch-off region, electric field is changing so rapidly, we cannot ignore that anymore, that term anymore. Okay? Yet, at the beginning of pinch-off region, this term is still negligible because still belong to the gradual channel part between the source and pinch-off region. Is that right? So if this term is negligible, now we immediately can substitute the right-hand side by this term at the beginning of pinch-off region, and which is what we did. Now, what is this term equal to at the beginning of the pinch-off region at y equal to 0? Well, Vg is Vg, not function of y, so just Vg. VFB is VFB, 2 phi b is 2 phi b. What is the surface voltage at y equal to 0, or y prime equal to 0, at the beginning of the pinch-off region? What is the channel voltage? VD set, isn't that right? Is that right? Good. So that's how we did the second step. Now the third step really is simple now. You notice we can cancel out so many terms. Why? Because these two terms identical, these terms identical, these terms identical. Do you see that? Yes? So we end up with d squared v dy squared equal to v minus vd set. You see? V minus vd set over 3 times Tox times xj. Xj moved to the right-hand side. Following what we're doing? Yes? All right. Can you see where xj appear in this term? I kind of did not call your attention to that. Well, because that has to do with the surface area of vertical surface, right? Surface area times the E is what gave us the electric flux going into the Gauss box. All right? That's why xj appeared here in the first place. Yes?
Where have you used that d dy dashed is very small?
D, E, Y, D, Y prime, yeah, D, E, Y, D, Y prime is very small. That's exactly right. And this is an approximation good in this portion of the channel. I'm running out of this portion. Between the source and the beginning of the pinch-off region. All right?
When we solve for the pinch-off region,
yes,
then we don't use that anymore.
We don't use that approximation. We did not assume that. You see, we kept that term. It's here. It's here. We kept that term. We kept the dy prime. This is the dy prime. But it's a very clever way to get rid of the qm. It's by evaluating this at y prime equal to 0. At that point, this term is negligible. So we just replace this qm whole term on the right-hand side with this at y prime equal to 0. At y prime equal to 0, this term is all known. Vg is known, VFB is known, 2 phi b is 2 phi b. This is Vd set. So we replace right-hand side with that. Okay? All right. Let's now concentrate on this. Take a look and appreciate how simple it is, right? Because beyond this, I'm going to give you the solution now. There's no more derivation. We're coming to the end of derivation now, right? Okay. So d squared y dy prime square equal to v minus vd set 3xj Tox. Now to simplify this, we're going to replace the variable. We replace the v with v minus vd set. So it becomes d squared v minus vd set. That's trivial because vd set is not a function of y prime. You can definitely do that. Equal to v minus vd set over L prime square, where L prime is equal to this, right? L prime is that characteristic length, right? It's a characteristic length, right? I add a prime to differentiate from the L that we used in the drain-induced barrier lowering analysis, right? The difference is, in that case, we had xd max here. Remember? We had, what's xd max? Yes? Today we argued why xj would be a better approximation if we're only dealing with a region very close to the drain. Right? You following what I'm saying? Okay? So we call that L prime, just to differentiate these two characteristic lengths. But other than that, the equation is very similar. And what would be the general solution for this equation? What form? Last time we saw hyperbolic sine cosine, right? This time the same thing, hyperbolic sine cosine, right? So the solution would be v minus vd set is equal to a hyperbolic sine y prime over L prime plus b hyperbolic cosine y prime over L prime. Is it okay? And to remind you, L prime again is square root 3 xj tx. Now we're going to determine a and b by applying the boundary conditions. First boundary condition, y prime equal to 0. I don't have a sketch of the geometry here for you. I hope you remember now. Y prime equal to 0 corresponds to what point in this problem? Beginning of the pinch-off region. Great. And if you said beginning of velocity saturation region, you get extra point, right? So beginning of velocity saturation region, all right, is y prime equal to 0. At that point, what do we know about v? V is equal to vd set, isn't that right? That's our old concept, right? Velocity saturation begins, we call that point vd set, right? That point is vd set. Is that right? Okay. You know, before we reach the vd set point in the channel, velocity has not saturated. Once we reach the vd set point, we enter into velocity saturation region, right? So we know at y prime equal to 0, this equation should be equal to vd set. Well, you substitute y prime equal to 0 in here. The first term is 0 anyway. Hyperbolic cosine 0 over L prime is 1, right? So that just means b is equal to vd set. We determine b now. b is equal to v. Oh, sorry. We determine b is equal to 0 or b equal to vd set. No, yeah, b equal to vd set, right? 0? How did I do this? Oh, I'm sorry. There's a vd set here I didn't see. Sorry about that. So this says b has to be 0, right? Okay? All right. So we take that away. We end up with only this now. So to apply the second boundary condition, which is a electric field boundary condition, we differentiate this both sides once to get electric field. All right? So left-hand side becomes electric field because we differentiated, right? Yeah? So first of all, field is equal to minus dv dy prime. So we'll now differentiate this. dv dy prime. Differentiate the second term is 0. Differentiate the third term. Differentiate, well, different this term, that term. And again, at y equal to 0, let me, oh yeah, that's right. Since b part is already out, so we only have one term to differentiate on the right-hand side. And it's equal to a over L prime, hyperbolic cosine, y prime over L prime. Is that okay? All right. Now we apply the boundary condition, which is E at y prime equal to 0. Now I want to ask you a question. What is the proper boundary condition? What do you know about the electric field at the beginning of the velocity saturation region? What do you know about electric field there? Very good. Velocity saturation region is the point at which velocity saturates. According to our piecewise model, at what field will the electric field saturate? I mean, will the velocity saturate? When electric field is equal to E set, right? So we know at that point, electric field is equal to E set. All right? And on the right-hand side, when y prime equal to 0, right side is just A over L prime. So we therefore know A is equal to E sat times L prime. Now E sat is a known constant. L prime is known. L prime is this. So we now know A. So here's our answer. V is equal to VD sat plus E sat L prime hyperbolic sine Y prime over L prime. Okay? Are you still with me? All right? All right, now here's the interesting picture. So the thing is, if we plot V versus Y, this is what we expect. If 0 is, this is Y, not Y prime, by the way, all right? This is Y, right? We know the voltage at the source is always 0, right? Then it rises somehow, and we're not talking about that today, but from previous review, we know voltage will rise somehow. Up to a point, we start the pinch-off region. At that point, what is V equal to? Very good, VD set. And at that point, using today's coordinate, what is Y prime equal to? This point is called Y prime equal to 0. Very good. Thank you very much. What we have done today is we found a way to extend this curve, right? It's continuous not only in this V plot, also continuous in the slope, because we even managed to make the electric field continuous. Is that right? And yet it rises rather rapidly, in fact, almost exponentially. That's hyperbolic sine cosine. Is that right? My question is, remember how we started this, what motivated us to do this question, is find out how long is the pinch-off region. How long is the pinch-off region? How long is that pinch-off region? How am I going to find that? We have to find at what point will this voltage be equal to what? VDS. That will tell us how long this pinch-off region is. Isn't that right? Is that right? All right. Mathematically, what we do is then we equate, this is the equation for V. Now we're going to say, what we know is that when Y prime is equal to delta L, we don't know what delta L is. We're going to find the expression for delta L, right? All we know is that when Y is equal to delta L, VD should be equal to VDS. Is that right? And VD should be, let me add a term, should be equal to VDS. Is that correct? Is that right? And that VDS should, that VD on the other hand is also equal to VD set plus E set L prime hyperbolic sine delta L over L prime, correct? So here we repeat that. VDS is equal to VD set plus E set L prime hyperbolic sine delta L over L prime. Yes? Now, will these two allow you to get expression for delta L? The fact that VDS is equal to that, will you be able to get an expression for delta L? Does that make sense? The next step? All right? Yes, exactly. All right? Now, maybe arcsinch, maybe some function that's difficult to visualize. No problem. I just remind you, sinh itself, we often approximate as exponential, right? So therefore, arcsinch is approximately what? Logarithmic function. All right? So now we know delta L is a log function of VD. Now that probably is something you have never thought about, right? But now you know, right? So delta L is a log function of the VD. Okay? And everything's fine. For example, when VD is equal to VD set, delta L is equal to 0. That's great. All right? And delta L increases logarithmically with increasing VD from the VD set. All right? Second thing is delta L is proportional to L prime. Now that's a very interesting point. If you want to design a transistor with very little channel length modulation, that means with very small delta L, what do you have to do? What do you have to do in order to get keep the delta L small? They won't? What would you say?
actually two kinds of things. One is decreasing the oxide thickness, and another is reducing the junction depth.
Absolutely right. Decreasing junction depth, decreasing the oxide thickness. So here you see another reason we want to scale the oxide thickness, to scale the junction depths, right? If we don't do that, IV curve might look like that, right? This is very arbitrary hand drawing, of course, right? See what I'm talking about? Yes? All right? Okay. So all makes sense. And by the way, this definitely is in agreement with what experimentally is known. For those of you that might know this, well, even if you don't know, you can probably believe me. If we make very short channel lengths today and still use the very thick oxide or deep junction, you can probably imagine IV curve will look like that, right? Kind of, won't show you a transistor curve. Looks more like a resistor. And that's exactly right. Okay? All right. And okay, the only other thing we haven't talked about is that, okay, so delta L increases VD minus VD set. But in log term, the argument should be dimensionless, cannot be voltage. So VD minus VD set should be divided by some voltage. And voltage turns out is equal to E set times L prime, all right? The L prime dependence here in this term is minor. The L prime dependence here is important. Okay? All right. Any question about this model for the channel length modulation? Okay. Now you see the full model, but we all agree that we don't like complicated equations, and arc cinch is still a little bit too complicated for us to use. So we're going to give you a simpler form. The simpler form is not in the form of delta L, because no one really wants delta L. I mean, of course, it may be nice, but what we really want is this R out, this output conductance or output resistance. Let me first introduce to you this quantity called R out, and then we'll try to give you a simplified form for R out directly, right, rather than delta L. Delta L turns out it's not something you need to remember all the time. It's just the cause of a problem itself is not a problem. The problem is this ID, VD, doesn't saturate very, very nicely. In other words, the grade slope is too large. So let's define something called a GDS. And we're not defining, many of you probably know this. If you know this, it's great. If you don't, just know this is a common definition. Something called a GDS, the name would be source drain source conductance. It's defined as DID DVD, DID DVD, DID DVD, called a GDS. GDS, of course, has a meaning in both the so-called linear region as well as the saturation region. But both for our purpose this semester, this class, this hour, especially as well as, usually, let me not make that statement. Just say for the purpose of this hour, certainly, we're only interested in the GDS in the saturation region, all right? What happens in the linear region has already been done. We already derived that. We're dealing with saturation region now. In saturation region, we're going to analyze its conductance, all right? Okay. Now, it turns out, very often we don't even talk about the conductance, we talk about the resistance. I'll give you an reason why in a moment, but bear with me. The output resistance defined as the inverse of the output conductance, 1 over G, all right? Okay? Now, if you plot this output resistance as function of VD, this is what you see typically, all right? Again, this is hand drawing, so don't take too literally. I probably would prefer to, change this to make this a little bit more gradual, I guess. I would prefer that, but you don't have to worry about this. Don't bother with changing it. Okay. Typically, what you see is that first, this output resistance is fairly small, which means the gradient is large, which is here. Slope is large, linear region. We're not worried about it. All right? And then this output resistance rises fairly rapidly. That's when we transition from the linear region to the saturation region. Is okay? All right? Then we actually kind of peak over region, fairly flat. By the way, this is where the analog designer would really like to use this transistor. You get very flat output IV characteristics, large R out, that's good. And eventually, this current slope start to increase again, and R out will drop. So sometimes this curve is set to determine the dynamic range. You can only operate your circuit, your transistor, in a certain VD range. Outside the VD range, your R out is too small for you to make a good circuit with. Okay, the transistor is not good for making a high gain circuit. All right, so this is the general characteristics. And so therefore, this is really where we can design good high gain circuit. And that's why we like to plot this in R out. If we plot G out, guess what this curve is going to look like? Where it's really most interesting, it's almost zero. You don't see it. The curve mostly is emphasizing where it's not interesting and not useful. Is that right? What's really interesting is important. We want to emphasize that point. Therefore, often you see data presenting R out rather than G out. All right? But in circuit design, circuit designers use G out just as often as R out, maybe even more. Okay? All right. Because mathematically you can use either, doesn't matter. But when you look at the data, R out is certainly emphasize useful data better. Now the reason it's important is because the product of R out and GM, we know what GM is. GM is transconductance, DID dVG. The product of this give us something called voltage gain. And for those of you who specialize in circuit design, of course this is trivial, but let me just briefly mention this for those students who are not EE majors. This is the way to think about why it's important to have a small slope here. First, let's think the slope is 0, all right? Perfect transistor, slope 0. And we have two curves, one for VG, one for VG plus delta VG. In order to make an amplifier out of this transistor, what we do is we connect the transistor in series with a resistor. And the way to describe the series connection is to draw the IV curve of the transistor for the two different VG and draw another line called a load line whose slope is equal to the resistor value. And this two intercept is going to give us the two output voltages, VD and VD plus delta VD. The way the circuit works is that by applying a small delta VG, hopefully we'll get a very large delta VD. You can do that by making this load resistor very large. You can do it that way. All right? Okay. Two things happens. First of all, we don't even use resistor for this purpose. We just use another transistor to sort of try to function that. And turns out the effective resistance value of that transistor has to do with the slope. I'll give you another reason for that. Let's just say we do have an infinite resistor here. Let's say R is infinity. If R is infinity, supposedly we'll get infinite gain. Is that right? With very small delta IG, we'll get very large delta VD. Yes? But in reality, that's not the case. Because in any real transistor, there's always a finite output conductance. You see that? I may be exaggerating it, but it's finite. So when you have that, even if you manage to find an infinite resistor, you still only get finite gain. Is that right? And that gain turns out is equal to this, the finite gain. So the maximum gain you can ever get out of a transistor, if it has finite output conductance or resistance. All right? So that's why it's very important to know R out. We all know why it's important to know GM, but R out is just as important as GM. Yes?
Is this gain a function of the VG itself?
Now let's do that, right? Why do we want to model delta L? Because we want to be able to have a quantitative understanding of R out. So let's look at that now. Okay? We're going to put what we just derived now into this R out and try to get that. Okay? All right. How to get R out? Well, first we have to substitute the Well, maybe I'll just show you the previous equation. You know, we have found expression of delta L as function of VD. Is that right? Is that right? That's the just previous slide. There's no need to go back. But just if you can just hear me, that's good enough. We already found expression of delta L as function of VD. Is that right? Earlier, we also argued that ID set is function of delta L. So now we know ID set is function of VD, I'm sorry. Now we know ID set is function of VD. Is that right? Is that right? If we know that, we can certainly differentiate dID set dVD. Can we do that? That will give us G0, right? Right? Yes? That would make a very nice homework, but I'm not going to do that with you in the lecture because it's a little long, right? We had expression of delta L as function VD, which has hyperbolic sign, right? We had delta L as function VD, yeah? And now we put that in this equation, which is also kind of long, right? So when you differentiate that, it's going to take a while to do it, right? Okay, but it's doable. And if you can, keep a clear head, which terms are negligible, which terms you have to keep, eventually you'll be able to come up with some kind of approximate result for G naught or R naught. So here I'm just giving you an R naught. Output resistance. Turns out it's approximately equal to channel length divided by the characteristic length, VD minus VD set divided by ID set. Okay? All right? Okay. If you would like to try this for fun, tell Kevin, and he can give that to you as a homework, okay? So, but only if you like that homework problem. So if you do this differentiation, you can always come with your approximation depending on what assumptions you make. But with certain assumptions, one can end up with something like that. Now that's very nice. That's simple enough. That tells many things. First, let's remember what do we want out of R naught. We want R naught to be large or small? Large, okay? Large R naught is good. Large R naught means very small slope. We want this to be large, okay? So how can we get large R naught? Number one, use long channel transistor, which is correct. Maybe trivial answer, but it's correct, all right? Anytime the channel length is longer, doesn't matter what delta L is, you're not going to change your current that a lot. Is that right? Okay? All right. Second, this is probably the most important conclusion from this model, is you want L prime to be small. Does that make sense? Sure, because delta L is proportional to L prime. Remember what we just did the 2 slides ago, or maybe 1 slide ago, 2 slides ago? Delta L, the pinch-off region length, is proportional to L prime. Remember that? Right? And day 1 told us in order to minimize delta L, we want to use thin oxide and shallow junction. So here we just find out that to get large R out, we want small L prime. And in fact, in a way, it also makes sense that the ratio of L, capital L, and L prime is important. In other words, the ratio between channel length and delta L, that's important. Right? Kind of makes sense. Now, this is probably the interesting part. That certainly, without this model, will be hard to visualize and to guess. We're saying this R out is supposed to increase linearly from a very small value at VD equal to VD set to a larger and larger value. First of all, it should not be surprising because we know when we just barely at VD set, just beginning pinch off, actually that slope is not very small, right? Right? And eventually gets smaller. Is that right? We all know that. Right at VD set, the slope is not as small yet. Remember, the beauty of this model is it's even continuous, right? All right. We know that slope cannot be too small. Eventually, we're going to get better, right? So it should increase with VD, but we don't know what form. But here it tells us is linearly proportional to VD. Okay? All right? Now, this gives us actually a little bit of a problem. If we now go back to the data, R naught or R out versus VD. The only part that you see this linear is this transition between the so-called the linear region and the saturation region. Where we are peak, where we really design our circuit, we try to operate the circuit, it definitely is not linear function VD. What do you get out of this? There are only two possibilities. One is that this equation is not good. Maybe I made too gross approximation to end up with this expression, right? That's why it's not a trivial question for you to derive this again. Maybe this is too gross. But if this is correct, if the approximation made to end to this point is appropriate, then there's only one other possible conclusion. That is, the peak RL is not limited by Chenming's modulation. There's a second mechanism. Now that, to me, is a more interesting lesson here. I hope that is the correct answer, and because it's more interesting. That means, next time people ask you, what is limiting this output conductance, what's limiting the gain of the circuit, it's not Chenming's modulation. All right? We'll talk about what it is next. But for right now, I just want you to appreciate that based on this model, one can actually conclude that Chenming's modulation is supposed to do this. We should be designing fantastically good high gain circuit if it's only Chenming's modulation. Is that right? Okay? So this is still not a trivial question. For example, one student, Mark Cao, tells me that he doesn't think this is right. He actually thinks this equation is not right. So I don't know. But at this moment, I'm assuming this equation is right, then this is not Chenming's modulation. Okay, we can talk about what it is next. But I just want to see if you understand this discussion and why one could draw the conclusion this part is not governed by the Chenming's modulation, because it did not follow what the theoretical behavior of Chenming's modulation. Is okay? All right, great. And if it's not, then we have to ask the question, what else? In other words, according to Chenming's modulation model, the slope eventually should be much smaller than what we see. That's really what we're saying. In reality, we don't. We see a larger slope, and secondly, also it's more linear than this model would predict, because this line is more or less independent of ED. That's the meaning of more or less a constant R out independent of ED, meaning the slope is independent of ED. Is that right? That means it's almost a straight line. And for those of you that have done circuit design, look at this carefully, it's pretty good approximation. It's pretty much a straight line. All right? That is, slope does not change with VD, whereas the Chenming's modulation mechanism would predict that slope should constantly change with VD, or decrease with increasing VD. All right? So if it's not, then we have to think what other mechanism can cause ID to increase. So Chenming's modulation is not responsible for it now. Let's assume something else dominates here. What else can make ID increase with increasing VD? Something that you already know. To think about it. What could be changing as we change VD? And as a result of that changing parameter, ID increases. I have a hint. The hint is I wrote DIBL here. With this hint, can you think, how can you explain why ID increases as VD increases? It's not Chenming's modulation. Channel is fixed in length. What could be happening? Yes? Wonderful. Complete the sentence, please. Speak into the microphone. All right? All right. As VD increases,
Lower threshold voltage?
VD decreases. That's called a DIBL. As VD increases, VD decreases. All right? That's called DIBL. And therefore, as VD increases, VT decreases. And therefore, current increase, right? Because current is proportional to VG minus VT. Yeah, that makes a lot of sense. And in that case, is it also reasonable that this line is linear? Because Vt to the first order, by the way, I should ask this question, test you if you remember, to the first order, what's the relationship between Vt and Vd? What's the relationship between Vt and Vd? Is Vt exponential function of Vd? Someone's nodding her head. That's not, but you get the partial credit because you're thinking of Vt as exponential function of L, channel length. But Vt is a linear function of Vd, remember that. And we argued that with the capacitor coupling concept. Vt is or delta Vt is linear function of Vd. So as Vd increases, Vt decreases linearly, therefore current increases linearly. Make a lot of sense. Is that right? So that would predict a constant slope. Is that right? Yes? Yeah. So to me, it's very reasonable assignment. This part is channel length modulation. This part is DIBL. Okay? And then later we'll talk about this part, what is responsible for this part. All right? But let me tell you, most of this transistor we use today, at least up to 0.18 micron, at least if you get it from TSMC, for example, because it's general purpose transistor, you really don't see this part. They design in such a way that this is not coming in, all right? But if you look at some really aggressive designed transistor optimized for digital circuit, of course, this could be quite severe. In other words, we could be operating where the slope start to increase. Okay? All right. Okay, any question about this R-out model? Now we have a complete R-out model now. The linear region, easy. Then we'll get into the transition region, and Vd not too much larger than Vd set. It's caused by the dominated by channel length modulation. Eventually, drain-induced barrel lowering determines output conductance, and therefore determines the gain of the transistor. Okay. Eventually, it's impedanization. We'll talk about that later. Yes.
So, as a circuit designer, we'd like to know what is the voltage beyond VD sat.
That's right. That you can use. Very
well,
good.
Actually, as an analog designer, we want to know at what point do we get to the high output impedance?
Very good. In other words, you really want to know about this branch.
No, not necessarily. We want to know how to.
Oh, how far you have to go in order.
Yes.
Well, you have a quantitative model right here. All right? Of course, this model could mislead you if you don't consider there's another thing that clips it. You might predict this keep on going up, right? But certainly this will tell you you cannot stay too close. You have to be how far up, right? So you do have the model, okay? All right. Let's start with you.
Okay. Can you help me physically understand why for channel length modulation R naught is linearly related to L, or I'm sorry, to VD?
Channel length modulation.
Yeah, for the linear channel length modulation part, why would R naught be linearly proportional to VD? I don't quite see that.
Channel length modulation R out is linearly proportional to VD. It is.
But an intuitive physical reason.
Yeah. I don't have a physical reason for you. This is just taking the Taylor expansion of the first order term here and there. That's what the approximation made, right? As I said, you may want to explore this more. If Kevin does not assign this as homework problem, maybe consider expanding on this as a term project. Honestly, a lot of things can be done. Certainly it's important enough topic as output conductance, right? Explore that, okay? All right. Okay. And the simple answer really is just the Taylor expansion. Somewhere we're just doing the differentiation and we start making approximations. At some point you get that. All right? But certainly it's different with this or with no VD dependence to the first order. Now that's two different, very different kind of expansion results, right? So it's even though it's a result, it's not a trivial result. You cannot say it's different from that independent VD. Okay? So when you make approximations, it's always good to know the physics, know which term is reasonable to neglect. Yes, question.
From that expression, we said that for a large R naught, we need a small L dash, and therefore we need a very small oxide thickness.
Yes.
But then the the oxide thickness dependence from ID sat is much more stronger
Go on.
than the Tox.
Go on.
So we would, if we take the Tox dependence from ID sat also into consideration, we would get the opposite dependence.
Okay, let's do one thing at a time. We all know how R is defined, right? It's defined as 1 over dId dVd. All right, let's just clarify on that. So as far as this term is concerned, there's no opposing effect. It's all included in the fact that ID already is a function of Tox is already included here. Okay, so if R out is the quantity you're trying to model, then there's no need to ask what does the oxide thickness do to ID. It's already included in here. Continue, please follow up.
I'm just confused because ID sat, if you write out the
Oh, I
expression
see what
for
you
ID
mean. Now you're talking about this term. All right, I'm waiting to get on this term. I'll get to that next, all right? But let me see if Barris has a question. You had a question or comment? Please, continue.
My question was why there's a linear dependence between ID and VT in this saturation region.
Between ID and
We said that
VD.
yeah, as VT changes like linearly, then ID changes linearly.
You question why?
Yeah, I
All
was
right,
thinking
very
about
good.
why. Is that
Let's
due
settle
to
that question. In fact, I'm going to answer that question together with the question that I think let's see. This is I think this is must be what Joseph was also thinking of, right? Joseph was asking, you know, as a circuit designer, you would like to have an idea what these output resistance are. And I already said for this branch at least, you already have this equation right here. So now I'm going to hopefully make you agree that we also have an equation at hand for this branch also. You have both branch, of course, then you know the entire picture. All right? And this, when we look at this branch, we'll also answer the question why it's linear function, why this is a constant. All right? So I have a little bit of DIB analysis right here. Okay, doesn't have to use more than this. Okay, G naught is defined as a DID sat dVd, remember? Is that right? Use chain rule, therefore it's equal to dVt dVd and DID sat dVt. Is that right? The first differential, you all agreed how you can do that. You can, based on what we did 2 hours ago, 2 lectures ago, delta Vt is a linear function of Vd. So that part is easy. Yes? All right? It's exponential function of L, but we're not talking about L dependence right now. All right? Okay. Second term is a Barris term. He didn't quite see how to relate the ID set versus Vt. The trick there is to realize that ID set is not a function of Vt, it's not a function of Vg, it's a function of Vg minus Vt. You see, every place where Vg appears, Vt goes with it in this form. Every place where Vt appears, Vg shows up. Therefore, do you agree that dID sat dVg, therefore dID sat dVt is equal to minus dID sat dVg? Do you agree? Just because these two terms, Vg, Vt, always shows up together in the ID set expression. Agree? This fact remains unchanged even with our more accurate model with velocity saturation. Yes? Remember that? Okay. It's always Vg plus Vt. All right? Okay? So therefore, we know dID sat dVt is nothing but minus Gm, because dID sat dVg is equal to Gm. Yeah? So very simple. So now you got a model for this branch, for the Dibble branch. R out is simply equal to the inverse of this, of G out. Any questions? Yes, Joe. Microphone, please.
So is G out negative?
Don't force me about sign, please. All right. Anytime it's a multiplicative term, I don't want to think about sign, all right? All right. You think about sign. All right. Any other comments or questions? All right, since I still have 5 minutes to kill, I will work through the sign with you. All right. Okay, let's do this. Okay. All right, let's see. We all expect G to be positive, right? Okay. dVt dVd, is that a positive number or negative number? Okay, so that's the answer, must be. Okay. As Vd increase, Vt drops. That's number. Okay. Very good. Any other questions or comments about what we talked about today? What we did today basically is the model for the IV curve in the saturation region. All right, we spend most of time working out this channel length modulation model, and certainly it's very different from p-n junction depletion region length model, which is what some people like to think is what determines that delta L. Is not at all. It's a logarithmic function of Vd, and it's let's say, okay, then we introduce this concept of output conductance and output resistance. And output resistance in some ways is the finale of this lecture, and turns out to be proportional to the channel length, proportional to Vg minus Vt, inversely proportional to square root of Tox and Xj, and inversely proportional ID set. Now this reminds me, I haven't talked about this term yet, so let's talk about this term in R out. The ID set dependence. It so happens if you do this analysis, you find out ID set R out is inversely proportional to ID set. This is probably not too surprising. Well, I would not say surprising or not surprising. Well, I guess it's not surprising because, when you differentiate this, all right, when you differentiate this ID set with respect to Vd in order to get GL, you know what you're going to find? You're going to find a lot of terms like this term is going to be proportional to this GL will be proportional to W, proportional to mu, proportional to Cox, inverse proportional to L, right? You can imagine you're going to get those things, which means what? Which means this is going to be proportional to ID set naught, maybe, that is right at Vd set. You see that? Yes? Yeah? So it's not surprising that we're going to find out RR will be inverse proportional to ID set. Is that right? Yes? Because if you differentiate this with respect to delta L, you're going to find that differential is proportional to W, proportional to mu, proportional to Cox, maybe proportional to Vg minus Vt squared. Is that right? Which means what? Which means ID set. Is that right? Okay. So it's not surprising that we find R to be inversely proportional ID set. Okay? Now this turns out to have a very important implication. If R out is inversely proportional to Vd set, yes? Yes? To inversely proportional ID set, right? Okay? What that means is that if we look at several different Vg curves, different Vg, each of them have different ID set, is that right? The one with the larger ID set, namely larger ID, by the way, the one with larger ID, namely larger ID set, would also have a larger gradient, larger slope. Is that true? Yes? If the slope is proportional to ID set, that means they will extrapolate to one point, correct? If the slope is proportional to ID set, that means you can extrapolate them back to one point. That's right? And this is a great simplification of the mathematical model for this. Today, the model we talk about is a really physical model. We can be very proud of it. It's not just curve fitting, right? So really physically, we know what's going on. But if you don't know the physics, but just by knowing they can extrapolate to one point, it's already useful for circuit design. You just say, I just measure this point and call this point a VA. A for VA stands for early voltage, right? And then you just draw a straight line from this point back to Vd set, and you end up with the correct slope for the output resistance. Do you follow what I'm saying? Okay. Now this is a fact. This is not very useful from physics point of view, although we can explain now why they have the right slope. because of this portion of that. Okay. By the way, this quantity, the output conductance due to the DIBL, I'll leave this as an exercise for the reader. See if you can prove that also roughly is a inversely proportional I set. Okay. So the fact is that you can extrapolate them back more or less one point. Okay. Now in reality, this is hard to say what you can or cannot, because this line is not exactly flat. So where do you do that extrapolation? But if you believe you can extrapolate to one point, you can always roughly find some linear lines through them and get to one point. And if you do get them, at least there is some theoretical justification for that. Okay? All right. So this is a common way to a mathematical model for the output conductance, and this behavior is also called early effect, early voltage. Even though both those two terms, early effect, early voltage, originally was used only for bipolar transistors. Today we also use them for MOS transistors. Okay. All right. If there are no questions, we'll take a break here, 10 minutes break, and we'll continue with the discussion session. All right, let's make 5 minutes break, because you guys always come back before 10 minutes.